Hello, it's Valentine from Simplistic, and we're going to take a look at an interesting problem using ice tables, but the calculation is going to be a little different from what we've been doing so far. So first we're going to, first of all, we have this equation. 2H2S gives us 2H2 plus S2. Kc is given to us. Notice carefully this Kc is very small because it's 10 to the negative 7. And we have some initial concentrations given to us, and we have to find the equilibrium concentration of S2. All right, so the first thing we need to do is let's go ahead and set up our ice table. So initial change and equilibrium, ICE, there's the ice. Let's write out this equation. I'm going to move this a little lower to give us a little space to write out the equation. We have 2H2S gives us 2H2 plus S2. All right, and then the initial quantities that are given to us for H2S is 0.100 molar. For H2, it's 0.100 molar, and for S2, it's 0.000 molar. All right, and what we have to do next is understand, first of all, is this equation moving to the right, or is it going to move to the left? And the reason we need to understand that is because we actually have, if we write it the way it's written, we actually have some amount of product. And even if you flip this around, so if those are the reactants, then we have some amount of product in this case. So whichever way you look at it, we don't know if the reaction is going to go this way or if it's going to go this way. So to determine that, let's go ahead and calculate the value of QC. Okay, so QC is equal to, let's go ahead and express it the way it's expressed out here. So what I mean by that is these are the products and these are the reactants. So it's going to be H2 raised to 2 times S2 over H2S raised to 2. And let's plug those values in. 0.100 for H2 square times S is 0.00 over 0.100 square. And because we have a 0 out here in the numerator, the whole expression becomes 0. So when QC is equal to 0, what that means is that the reaction is going to proceed to the right. Because the only time it's equal to 0, it means that you don't have sufficient products out here. Okay, so it has to proceed to the right. That means the way we wrote the reaction down is the correct way. All right, so now let's go ahead and come back to our calculation. So the change out here is going to be negative 2x because it's proceeding to the right. You're going to have positive 2x of H2, and then you're going to have x for S, and then at equilibrium, we're going to have 0.100 minus 2x, 0.100 plus 2x, and x. All right, so now once we have all these changes, let's go ahead and express it in terms of the equilibrium constant. So Kc is equal to, it's going to be the same expression out here. So I'm just going to copy and paste that out here. That is equal to this. And now I'm going to plug the values in. I'm going to erase that too. I'm going to plug the values in. So Kc 1.67 times 10 to the negative 7 is equal to 0.100 plus 2x raised to the power 2 times x over 0.100 minus 2x raised to the power of 2. Okay, so once I have this, the next thing to do is to pay attention. You actually have an equation where the x's, if you multiply this whole thing out, you will actually notice you will get a term of x times x squared, which is x cubed. So that's a cubic equation. And while you can solve a cubic equation, it's not recommended you do that. So we're going to make an approximation out here. And the approximation is that since Kc is very small because of the 10 to the negative 7, the reaction, although it proceeds to the right, it doesn't proceed sufficiently. And what that means is, it doesn't proceed sufficiently means that this value of x is very, very small. Because the x is very small, we're going to assume that this x is so small that even twice of that x is much smaller than 0.10. So for all intents and purposes, 0.100 plus 2x or 0.100 minus 2x is equal to only 0.100. Okay, now bear with me because we'll check that approximation a little later. Okay, so I'm just going to go ahead and simplify this expression. So that's 0.100. That becomes 0.100 squared because I dropped the 2x, and the same thing happens at the bottom, 0.100 squared. Now because we did that, these two terms cancel out, so x is equal to 1.67 times 10 to the negative 7 molar. And that is the concentration of the equilibrium concentration of S2. So we're going to write S2 molar concentration at equilibrium is equal to this. Now let's test that approximation. So the way to test it is, whatever the solution for x is, which is this, if you take it away from the number that you're subtracting it from, is it going to be, whatever answer you get, is that going to be greater than 95% or less than 95%? Okay, so basically you can just think of it as compare this number to this number, and is this number less than or equal to 5% of this number? And if it is less than 5% of this number, then your approximation is correct. Okay, so I'll just write that down here. So x term should be less than 5% of number it is subtracted from. All right, so I'm just going to go ahead and take that S term and write it in standard notation, which is 0.000000167 molar. As you can see, it's a very small number, very small number. So we'll multiply that by 2, which is going to give us 0.000003. Let's approximate that, about 3.3. Okay, so I'm rounding out here. Okay, now if I actually have to, when I'm subtracting, I go with the least number of decimal places. So if I actually have to compare this with, I'm just going to put this over the number it was subtracted from, which is 0.100, 0.100. As you can see, there's so many decimal places out here, and if you actually take the ratio of that number, let me just go ahead and do that in my calculator, 0.0000033 divided by 0.100. So if I take the ratio of that number, that is 0.0000033. Okay, and if I multiply that by 100, that becomes 0.00033. So clearly that is much, much less than 5%. Therefore, our approximation is correct. Therefore, this is the equilibrium concentration of S2. I hope that made sense. Thank you for watching.